Hi, I'm Talha Khan from UT Austin, and in this talk I'll be discussing stochastic geometry analysis of downlink cellular with semi-static clustering. So it is well known that out-of-cell interference in cellular systems is a key performance bottleneck. However, base station cooperation can help combat against out-of-cell interference and improve the performance of the network. There have been a lot of research on base station cooperation and clustering schemes to combat intercell interference in cellular systems. Such clustering schemes could be broadly classified as static and dynamic clustering approaches. In static clustering, the base station clusters remain fixed over time. However, the performance is limited at the cluster edge users, as we will see later. In dynamic or user-based clustering, the base station clusters that cooperatively serve a user, they are formed adaptively, which results in better performance where it is more challenging to implement in certain situations due to signaling overheads. So let's consider static clustering first. So here we see a group of base stations denoted by blue dots. And for example, the 4 base stations within the green area, they could form a cluster to serve the users within these cells. However, this cluster would remain fixed over time and it is predefined. The problem with static clustering is that the performance of a user depends on the location of the user within the cluster. For example, if a user is located closer to the center of the cluster, then it experiences better performance because of lower interference from the other cell transmitters. However, if the user happens to be at the edge of the cluster, then its performance would be relatively poor because of more interference from the neighboring out-of-cell base stations. So static clustering, though simple to implement because the base station clusters once defined remain fixed over time, experiences poor performance around the cluster edges. On the other end of the spectrum, we have what is called dynamic clustering in the literature. Dynamic clustering is adaptive in nature and it is centered around the user. So for example, if we have a user at the cluster center on the left, and similarly we have another cluster such that the user is still at the cluster center on the right. So both these clusters are formed based on the user location, such that there's a user is served by a base station, by a group of base stations in a cluster in which it happens to be closer to the center. However, it could be more challenging to implement due to signaling overheads because unlike static clustering, which remains fixed over time, the dynamic clusters are user defined and they adapt over time. And dynamic clustering, however, does not suffer from the problem of cluster edge users as static clustering because the clusters formed in dynamic clustering are user centric. So in order to get the performance gains closer to what dynamic clustering has to offer while keeping the implementation as simple as static clustering, we can use what we call semi-static clustering. So in semi-static clustering, instead of using one predefined cluster, we could define multiple clusters and alternate between them. So for example, on the left is a green cluster, and on the right there is another cluster in orange. So in one time slot, the green cooperation cluster would be active, while in the other time slot, the red cooperation cluster would be active. And the users can associate with the user with the cluster in which it happens to be closer to the center. So this happens to mimic what is achieved by dynamic clustering. However, unlike dynamic clustering, the base station clusters won't be formed based on the user locations. They would be predefined, as we will see later. So to explain semi-static clustering, we show some random locations of the base stations, which would be the case in practice since base station topologies are irregular. So it's not obvious how to group these base stations into clusters. For analytical simplicity, we assume a square lattice to cluster the base stations. So for example, each cell of the square lattice is parameterized by a length r, and all the base stations that form within a square cell are said to constitute a cluster. And we use the term partition to refer to this collection of clusters or this lattice. So in this way we could obtain one partition for a given base station deployment. The next question is how to obtain more partitions, because as we mentioned before, in semi-static clustering the idea is to have multiple predefined partitions and you alternate between them. A simple idea is to shift the square lattice to get another partition of the base stations. So and a user can associate with the partition where it is more in center, and each partition would be used on alternate time slots. So for example, here we could see a user denoted by a green star, and there are two possible partitions, partition 1 or partition 2. Only one of the partition would be active in a given time frequency slot. So for example, in this case, a green user would like to be served when partition 1 is active, because it happens to be closer to the center of the cluster in partition 1. However, in partition 2, it is around the edge of the cluster in which it would be served. So in this scenario, green user denoted by the star would prefer to be served by partition 1. And each partition would be active on a given slot. They won't be simultaneously active in the same slot. And now we go through the user scheduling algorithm with such semi-static approach. So the first step is to assign a user to the base station. So we assume that a user is assigned to the closest available base station. And the next step is assigning partitions. So as you could see, the serving base station of the user can belong to either partition 1 or partition 2, depending on the time slot we are operating. So but only one of the cluster would be active in a given slot. So we would like to serve the user when partition 1 is active. So in this way we would, so to summarize, the first step is to assign a user with a base station, and the second step is to pick the partition in which that user would be served. Each base station belongs to two overlapping clusters. Only one of which would be active in a given slot. So we will serve this green user when partition 1 P1 would be active. So with this system and channel model, we used tools from stochastic geometry to characterize the outage performance at such a user when served with semi-static clustering. So in the next section, we will go through the channel model at the user and the type of cooperation we are assuming. So here on the right is just a snapshot of a cluster from a partition, and k denotes the number of base stations within a cluster, and it is a random variable because of the Poisson topology for the base stations. So here we could see 3 base stations serving 3 users. Now for a typical user, this is the equation for the received signal. So we assume that the base stations within a cooperating cluster use intra-cluster interference nulling to serve the users within the cluster. That is to say, it pre-cancels its interference to other users belonging to the same cluster while serving its own target user within the cluster. Here we have assumed that each base station has sufficient number of antennas to perform intra-cluster interference nulling, and it also knows the channel to the users within the cluster. However, this transmission strategy does not require joint encoding between the transmitters belonging to a cluster. So to summarize, in this equation we could see that a user receives useful signal from its serving base station, no intra-cluster interference from other base stations belonging to the same cluster. However, it experiences out-of-cluster interference from all the base stations outside its own cluster. And we further assume the links to experience IID Rayleigh fading. So this is the expression for the complementary cumulative distribution function of the signal to interference ratio at the receiver, conditioned on its location and the link distance to the serving base station. So as you could see, it is a function of the parameter r, which we define to be the length of the cluster square cell, and theta is the outage threshold. Eta is the path loss exponent, and this should be theta raised to minus eta by 2 by eta. It's a typo. And the exponential on the right, it involves an integration over a square box of side r and center mu, which is numerically easy to evaluate in practice. And here we also, to validate this expression, we also plot the outage probability at a receiver as it moves from one edge of the cluster to the other with other parameters fixed. So there is a nice match between analytical and simulation results, and it also corroborates our earlier claim that static clustering performs poorly around the cluster edges, because as you could see that around the corners of the x-axis, which corresponds to the user being closer to the cluster edge, the performance is very bad, and it's best when the user is near the closer to the center of the cluster. So in using this analytical expression, we also wanted to characterize the behavior of the outage probability in terms of the cluster size. Remember that the length of the square cell R is also a proxy for the number of base stations in the cluster, because as R increases, the more number of base stations are likely to be there in a cluster cell. Our analytical result shows that the outage probability at a user scales with the cluster parameter, and the order of the scaling is determined by the path loss exponent. And this result applies to both static and semi-static clustering, because the expression we derived on this slide, it corresponds to both static and semi-static cases. So it's not particularly for the semi-static case. To summarize, the rate of decay of outage probability is determined by the path loss exponent, and it is applicable to both static and semi-static clustering. That is to say, the outage probability in both static and semi-static clustering scales with the same order, however with possibly different linear scaling coefficients, which we denote by kappa here. It would depend on the path loss exponent, link distance, and user location. And on the right, as you could see, with static clustering, your cluster cell would typically look like a square with bold black lines. However, with semi-static clustering, when you would be associating a user with either partition 1 or partition 2, such that it happens to fall closer to the cluster center, this effectively gives a cluster like a diamond, which is shown by dots here. So as you could see, in semi-static clustering, there is more protection from out-of-cell interference. However, it is still a square box, which is why the scaling is the same for both static and semi-static cases. So to further quantify the gain from semi-static clustering over static clustering, we defined a metric G, noted here, which is the ratio of the outage probability with static clustering to that with semi-static clustering, averaged over base station and user realizations. And we found that as the cluster parameter or the cluster size increases, this gain converges to a limit. This suggests that semi-static clustering only provides a linear gain. There is no order gain. And this follows from the previous result that semi-static and static clustering scale with the same order with the cluster parameter R. So here we plot some simulation results. So in this plot, we plot the SIR CCDF with static clustering, semi-static clustering, and a bound as well. So, excuse me. As you could see, semi-static clustering improves the performance over static clustering. This is evident by the CCDF of semi-static clustering. We could also see a bound in the pink curve, which corresponds to the case where every user is hypothetically served when it is served by the partition in which it happens to be closer to the cluster center. With semi-static clustering, it's not always possible to assign a user to its desired partition. And we can also see that the analytical expressions give a good approximation of the simulated results. The small gap is due to ignoring the special correlation in the analytical expressions, which is considered while simulating using Monte Carlo method. So in this plot, we plot the gain due to semi-static clustering over static clustering for different cluster parameters R as a function of the outage threshold theta. So we could see that the gain improves with the cluster size. This is because the users see reduced average interference. You can also observe that there is a diminishing, the gain diminishes as R is increased because most gain can be realized with a moderate R. And we can also observe that more gains are possible in the low outage regime, that is to say when theta is small, where most practical systems typically operate. And finally, to conclude, we analyzed base station cooperation in downlink cellular using a semi-static clustering algorithm and derived numerically trackable expressions for the SIR CCDF. We also looked at the scaling behavior of the outage probability in terms of the cluster parameter R, and found that the outage probability improves with the cluster size, and the path loss exponent determines the rate of improvement. And we also quantified the gain from semi-static clustering over static clustering. Results suggest that semi-static clustering only provides a linear gain over static clustering. No order gain can be attained. Thank you.
Okay, great.